Okay, test. Okay, so hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Material Science program at the University of Ontario Institute of Technology, also known as Ontario Tech University. So I also took my Bachelor's of Science in Pharmaceutical Chemistry at this institution as well. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then just check out the links in the description below. Okay, so we're going to get started with our set of questions for today. Okay, so the first question asks, what must the ratio, I'm assuming that's of, H2PO4 minus be to HPO4 2 minus have a buffer with a pH value of 7. So I'm assuming it just means what should the ratio of those two be to have a buffer with a pH value of 7. Okay, so this is question number 1. And then the first thing we're going to do, let's just write out the reaction that goes on. So we have our H2PO4 minus, the aqueous. It's gonna react with water, which is a liquid. And then it's gonna form H3O plus the HPO4 2 minus aqueous. Okay, so now we're just going to figure out which one's our acid and which one is our base. So again, let me just change the color. The H2PO4 minus will be our acid, and here the water will act as a base. Okay, so I'll just give the Bronsted-Lowry definition of acid. So it's the one that donates the proton. And then the base is our proton acceptor. Okay, and just for good measure, we'll also find out which one's our conjugate acid and our conjugate base. So after the H2PO4 minus donates one of its protons, then the H3O plus becomes our conjugate acid. And then this is our conjugate base. Okay, so you can see that already our question starts off with phosphoric acid that has already lost one of its hydrogens to have H2PO4 minus. So I need to find the Ka value for H2PO4 minus. So let me just look that up. Okay, so that's what it is for H3PO4, but we're looking for the one associated with the H2PO4 minus. Okay, so it's going to be this 6.2 times 10 to the negative 8 value. Okay, so after that, we can now calculate for pKa. To do that, it's just going to be negative log of our Ka value. So let's just plug the values in. Okay, so then you get a pKa value of around 7.2 for H2PO4 minus. So then the second step to answer this question is to calculate the ratio of acid to conjugate base by using the Henderson-Hasselbalch I think there's a K there. It's an H. Henderson-Hasselbalch equation. So you use this formula right here to do that, where pH is equal to pKa plus the log of the concentration of our conjugate base over the concentration of our acid. Okay, so I'm going to plug these values in. We want to have a pH of 7. We calculated the pKa to be 7.2. And then, since we're just looking for the ratio of H2PO4 minus to HPO42 minus, which is our acid and conjugate base, I'm just going to leave these as is. Well, actually, I'll just specify the compound. So our conjugate base is the HPO42 minus over the concentration of our acid, which is H2PO4 minus. Okay, so now we're just going to solve for this ratio just by doing some math. And then to get rid of the log, we're going to do 10 to the power of both sides. So it's going to look like this. So then we end up getting this value as 0.63. But I'm just going to write up here. The question's asking ratio of H2PO4 minus to HPO4 minus. So I'm just going to switch that around. So therefore, So it's gonna be 1 divided by 0.63 just to get the ratio of our acid on top. It's going to be 1.59. Okay, so let's look at the answer that our junior tutor wrote. So they have the Ka for phosphoric acid. Ka1 is 7.1. The second is the 6. They have 6.3, but I got 6.2. It doesn't really matter. They still got 7.2 as their pKa. And then next they use Henderson-Hasselbalch equation. They got the 0.63. And then they did the ratio that I did as well. They even took into account the significant figures. So this solution is correct. Okay, so solution is correct. Then on to our second question. So draw the major elimination product formed in the following reaction. So let me write down our starting product. Okay, so here our reagents used are potassium ethoxide, so potassium ethoxide is a strong base, and what I mean by that is that it's good at deprotonating. And then our DMSO is just the solvent. Okay, so I believe there are two products that you could get. I'll show the major one first. So I'm going to draw hydrogen there. And I'm just going to draw our base come in. It's going to deprotonate this hydrogen. This bond will form a double bond there. And then our bromine is the leaving group. So then the product that comes from here will look like this. So you see we have a new double bond that's right here. And then using different colored arrows, I'm going to show what happens if this hydrogen is deprotonated instead. So same thing's gonna happen. We're gonna have our base come in, deprotonate this. This will come down, and again, our bromine is gonna leave. But this time, the double bond is in a different place. So the first one is our major product, and this is because this double bond is in conjugation with the phenyl group that's there, so with that benzene ring. So that means that increases that product's stability. And then for this orange one, it's our minor product. So even though its double bond is on a more substituted carbon, this product on the left is still going to be our major product. Okay, so let's just see what our junior tutor wrote. Okay, so they also did the major product that I wrote. The alkene is in conjugation with the double bonds of the benzene rings, and therefore this conjugation provides stability. So this answer is correct. Okay, so the next question asks to write the pressure equilibrium constant expression for this reaction. So they're only looking for the expression, so we don't need to solve for anything. This is question number 3. So let me just write down this reaction. Okay, so let me write out the general rule whenever you want to solve for equilibrium constants. So I'm going to write down like a hypothetical reaction at the bottom here. It's a little confusing with letters, but basically your lowercase letter is the number of moles. So it's basically the coefficient that's in front of our element. And then the uppercase is our substance. And then the general equation for like equilibrium constants, I'll denote as K. Looks like this. Okay, so pretty much it's gonna be your products over your reactants. And then let me just write out that these are raised to the power of their respective coefficients. So in our case, everything has just 1 mole of it. So if we want to look at the pressure equilibrium constant for this question, I'm going to denote it as Kp. And then it's going to be the pressure of our products. So in our case, it's H2 and carbon monoxide over the pressure of our reactants. So PH2O, P of the carbon. But another important thing to remember is that because carbon is a pure solid in this reaction, it's going to be omitted from the final expression. So solids and liquids are omitted. And this is just because their activities are equal to 1. Okay, so then we get this Kp equals the pressure of hydrogen times the pressure of carbon monoxide divided by the pressure of H2O as our expression. And that is the same thing our junior tutor said. So the solution is correct. Okay, so on to question number 4. Identify the following processes as spontaneous or non-spontaneous. Explain your choice. Okay, so first I'm just gonna write down the definition of spontaneous. Basically, the system loses its free energy and then goes to a more stable and lower energy state. Okay, so let's look at A. A photovoltaic cell in a solar panel produces electricity. So what's happening is that the energy from the sunlight is absorbed, and then this is converted to electrical energy. And this is done through like redox reactions, but basically this is a non-spontaneous process. Okay, so let's look at B. Helium gas escapes from a latex party balloon. Okay, so this is spontaneous. And we know that because when the air is in the balloon, the inside of the balloon has such a high pressure that's involved. And then once the party balloon like has a hole in it, then the pressure starts to be relieved. So this process is spontaneous because they always want to try to go from a high pressure system to like a lower one. So that's why B is spontaneous. And the next one is a sample of pitch blende uranium ore emits alpha particles. So this is like a radioactive example. And typically the particles are removed, they're emitted spontaneously. Okay, so I'll just reword it as like an unstable high energy substance loses energy to reach a stable energy state. So that process is spontaneous. And then let's see what our junior tutor said. Photovoltaic cell in a solar panel produces electricity. Its energy content increases, hence it is a non-spontaneous process. During the escape of helium gas, no temperature change, entropy of the gas increases, hence it's a spontaneous. And then finally, radioactivity is a spontaneous process because here an unstable high energy nucleus loses energy to reach a stable lower energy state. So this solution is correct. Okay, so we have one more question for this session. Question number 5, which is, how much faster do ammonia molecules effuse than carbon monoxide molecules? Okay, so first I'm just gonna write down Graham's law of effusion. So basically it relates the ratio of the effusion the effusion rates of any two gases A or B through the following equation. So you can have the rate of gas A over the rate of gas B, and that is equal to the square root of the molecular weight of B over the molecular weight of A. Okay, so next we're just gonna sub in the molar masses of ammonia and carbon monoxide. So I'm just gonna write them over here. For NH3, its molar mass is 28.01 grams per mole. And then the molar mass of carbon monoxide is around 17.03 grams per mole. Okay, so I'm just gonna sub those values in. And then we end up with a value of around 1.28. So therefore, NH3 effuses 1.28 times faster than carbon monoxide. So let's look at our junior tutor's answer. They did the same equation. Square root of CO over molar mass of NH3. And then they got 1.28. So the solution is correct. So I think that's all the time that we have for today. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, then hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, don't forget to leave a like and comment if you like the video, and please share it with all your friends and classmates. This has been Donna from OneClass, and I hope to see you soon. Goodbye.